Hi, Professor Hoffman. Thanks for taking the time to talk to me today.
Hi, George.
How are you doing?
I'm okay. And you? You good?
Yes, very good, thank you. Yeah, very good, thank you, very good. So today I wanted to talk about turbulent flow. Predicting turbulent flow is widely understood to be a very hard problem. How can you rely on the results of a computational simulation such as CFD if you don't know what the exact solution is? And how do you know that you have the right solution?
Yeah, that's a good question because typically you're interested in a new problem which you haven't studied before, so you don't have an exact solution to compare with, as you say. So either if you have a benchmark problem, you can compare against that, and you can hope that your method should generalize also to this new situation. You could also perform, which is one of the more established ways, is to do a mesh study. So one parameter of your method is the computational mesh. So you run simulations on a range of different mesh resolutions, and if you get the same result, you consider your solution converged. But even if it's converged, that's not a guarantee that you have the right solution, right? Because you can have other parameters in the method. So another technique is a more mathematical approach, is that you have your solution and you can evaluate how well it satisfies the underlying equations, the Navier-Stokes equations, which describe fluid flow. So that's called an a posteriori error estimation. So this is something you can do.
Okay, excellent. So that particular technique, how did it lead to mesh refinement workflow that doesn't need a user at all, or a user input at all? What does that represent for traditional CFD?
Yes, so where traditional CFD mesh design is a very large part of the problem. So you use experience and heuristics to design a mesh which you think is appropriate for the situation. But if you have access to an a posteriori error estimation, then you can not only estimate the error in the output you're interested in. This could be the drag of a car or the wind load on a building. You also can localize the contributions to that error. So you know what part of your simulation domain, what part of the mesh that contributes to the error. So in doing that, you can also steer your mesh refinement to refine the mesh where needed to optimize the accuracy in the simulation.
Okay, excellent. That's very interesting to hear. We know that some users, especially CFD experts or experienced users of CFD, have a hard time dealing with automated tools, almost releasing the reins, because they have an understandable concern that they don't know what's going on behind the scenes. So is Ingrid Cloud a black box?
It depends how you would define that. So Ingrid Cloud is based on a method with very few parameters, because it is a transient large eddy simulation, meaning that we resolve all the turbulent scales. So it's very little to model. If you need to model unresolved turbulent scales, you need to introduce parameters, and then you need to know what these parameters should be. But in Ingrid, it's very few parameters, and the only real parameter is the mesh resolution. So you use adaptive algorithms to optimize the mesh to determine the mesh resolution depending on what you want to compute. So this leaves a parameter-free method.
Okay, excellent. Well, hopefully that's put some people's minds at rest, and they can start to explore our solutions a bit more. Well, I think that's everything for now. So thanks very much. I really appreciate your time, and hopefully we've given the viewers of this video some food for thought. And if they've got any questions or queries, I'm sure we'd like to hear them.
Sounds good. Thank you.
Excellent. Thank you very much.